Welcome to the seventh and possibly last screencast for Chapter 7, Covalent Bonds and Molecular Structure. Let's pick up with another example of shapes of molecules, and this time we're going to do SO2, sulfur dioxide. And as you've seen before, first of all we need to figure out what the Lewis dot structure is, so I'm going to give you a chance to pause and draw the structure of SO2. And hopefully you come up with something like this. Sulfur in the middle, oxygen on either side, single bond to one oxygen, double bond to the other oxygen, lone pair of electrons on the sulfur, and then of course note this is resonance, where the double bond could be to this oxygen or to the other oxygen. So the real SO2 molecule will not have a double bond and a single bond, but more like a 1.5 bond on this side and a 1.5 bond on that side, and of course the lone pair. Okay, now to get the shape we have to ascertain the number of electron groups, and again it's around the central atom, so you might want to pause and think about how many electron groups that will be. And hopefully you came up with 3 electron groups. Single bond is 1 group, double bond is 1 group, so that's a second group, and then the lone pair is 1 group, so that's a total of 3 electron groups. And then we can say, well, if we have 3 electron groups, what's the shape going to be? And note something here. In this case, we have one of the electron groups bonded to an oxygen, a second electron group bonded to an oxygen, and a third electron group not actually bonded to anything. And what that means is the shape is not one we've seen before. It's a shape that's called bent. So let's consider this a little bit. If we look at the 3 electron groups shape that we have seen before, which is called trigonal or triangular planar, we have 1, 2, 3 electron groups, but each of those electron groups in this shape is bonded to an atom. Well, what if one of those electron groups wasn't actually bonded to anything, it was just a lone pair? Then that wouldn't really be part of the shape. I mean, it would help form the shape, but it really wouldn't be a triangle that's planar anymore. And so if we have all 3 atoms connected, or all 3 electron groups connected to atoms, then this would be a trigonal planar arrangement. But if one of those groups is not connected to anything, then if it's just a lone pair, then we have a bent molecular shape. And so you're going to need to note that there are some subshapes of these sort of basic shapes, the linear, trigonal planar, tetrahedral, trigonal bipyramidal, and octahedral, and you're going to need to be aware of those as well. So let's look at this just a little bit, hopefully better. Now we're going to look at a top view of the SO2 molecule, and perhaps you can see the bent shape more clearly. There's an angle between O and S and O that's called the bond angle. It's about 120 degrees. And note, here's an electron group, there's an electron group, and then the third electron group is a lone pair. It does look like a triangle, except since this lone pair doesn't attach to another atom, it's really only this part that is the shape of the molecule, which is why we call it bent. Now, is this molecule polar or nonpolar? And again, we're going to look at this top view of the molecule. So a couple different ways of looking at it, sort of a ball and stick molecular representation and a drawn out SO2 molecule. And if we note that S to O is a polar bond, oxygen's more electronegative than sulfur, so we have a dipole from sulfur to oxygen, and we have a dipole from sulfur to the other oxygen. And note that in this case we have 2 dipoles, but they're not pointing directly opposite to each other, so they don't cancel out. So this would be something like imagining if you pull this direction and that direction, will this object, this molecule, move? And of course it would move a little bit to the right, And so we have an overall dipole from the sulfur to the 2 oxygen side of the molecule, if you will. And here's a side view. And so this is a overall polar molecule because the dipoles between the atoms that form the bonds, those dipoles don't cancel out. So here are the shapes and subshapes we talked about before, and these are the ones you should get familiar with. Linear doesn't really have a subshape, but trigonal planar has a subshape of bent, where one of the electron groups is not attached to an atom. Tetrahedral has actually 2 subshapes, so we can have tetrahedral, all 4 atoms, all 4 electron groups are bonded to atoms. But if one of the electron groups is not attached to an atom, it's a lone pair, then we have a triangle, but it's a pyramid, so we have what's called trigonal pyramidal. If we have 2 electron groups that are lone pairs and 2 that are bonded to atoms, then we have a bent shape, and so this is a bent shape. This is also a bent shape here, and the bent shape that's a subset of trigonal planar has an 120 degree bond angle. The bent shape that is a subset of tetrahedral has 109.5 degree bond angle, so they're not quite the same, but we still call them both bent. Trigonal bipyramidal has a seesaw, a T-shaped, and a linear subshape. Octahedral has a square pyramidal and square planar subshape, and these are things that hopefully you will get familiar with as you do more examples. So let's do another example. What's the shape of a ClF5 molecule, and is this molecule polar or nonpolar? So chlorine pentafluoride is the molecule, and what you want to do first, think about it a sec, and hopefully you would say, draw the Lewis dot structure. And the Lewis dot structure is going to be one that has 7 valence electrons for chlorine, 7 times 5 or 35 valence electrons for fluorine, 42 total, and you might want to pause and draw the structure. And it's going to look like this: chlorine in the middle, fluorine, 5 of them surrounding it. We're going to have to make bonds to each of the fluorines, so note we have an expanded octet, and that's going to be okay because chlorine is a 3rd row element which can expand its octet. That's 10 electrons. We fill in the rest to get up to 42, and lo and behold, we get nice little octets around each of the fluorines, but we have to have 2 more electrons around the chlorine, not bonded to anything, so we have 5 bonds and a lone pair to the chlorine atom. So what's the shape going to be? Well, you have to ask yourself how many electron groups you have, and we have 1, 2, 3, 4, 5 electron groups that are bonds, and 1 electron group that's a lone pair. So we're going to have 1, 2, 3, 4, 5, 6 electron groups around the central chlorine. And that shape looks like this. It's called square pyramidal. So it's essentially an octahedral. If we had an atom here, then we would have an octahedral shape. But since one of the electron groups is not bonded to anything, hopefully you can see the square base of a pyramid. And is this molecule polar or not polar? Well, if we go back to our Lewis dot structure and draw in individual dipoles, we note that chlorine is less electronegative, fluorine is more electronegative, and so we have 5 dipoles, and then the question is, do they cancel out or not? And notice we don't have a dipole to the lone pair, and so what we end up having happen is our individual dipoles don't completely cancel out, and we get an overall net dipole towards the top, if you will, fluorine that we have drawn in this representation. So the overall dipole is that way. Now this is kind of hard to see if it's on a flat piece of paper or flat screen, 2-dimensional, when it's really 3-dimensional. So let's look at the actual 3-dimensional representation, which is hopefully a little more easy to see that we have a dipole to each of the 4 fluorines in the square base that would cancel out, but there's a dipole upwards towards this fluorine atom that's not canceled out by a dipole down towards the lone electron pair, and so we have an overall dipole towards that. In this case, we'll call it the top fluorine. Okay, so a little bit of summary, and then that's it for this screencast. So some things to pay attention to. Remember that each single bond, each multiple bond, and each lone pair counts as an electron group when we determine geometry and shapes. And here are a couple examples as we've seen before. And then also note the difference between what we sometimes call electron group geometry and actual molecular shape. So here's an example of that again. We have 3 electron groups around the central atom in this shape, and we have 3 electron groups around the central atom in the shape below that. But this one, because each of the electron groups is bonded to an atom, that is a trigonal planar shape, and an example is shown to the right. But in the case of the lower structure, we have only 2 electron groups bonded to atoms, and one of the electron groups is not bonded to an atom. So we have 3 electron groups, but only 2 are bonding groups, and the actual molecular shape, therefore, is bent. And then also, of course, you need to be aware of the subshapes of the basic shapes, and you're going to need to know those as well, and by doing examples and getting some practice, that's going to help you the most. So planar triangular has a bent subshape. Tetrahedral has pyramidal, trigonal pyramidal, and bent subshapes. And here are the sort of summary images, and these are, of course, in your textbook as well. Linear, no subshapes. Trigonal planar has a bent subshape. Tetrahedral has trigonal pyramidal and bent both as subshapes. Octahedral has square pyramidal and square planar as subshapes. And then we showed you previously the subshapes for the trigonal bipyramidal, and you might want to refer to that in your book. So that's kind of the summary of the information and some examples for Chapter 7. And that's it for the official screencasts of that type. There might be some more examples if people want them. So hope that helps, and adios.